Thanks for the invitation. It's great pleasure to be in this series. So far, all talks that I was able to attend were great. So one comment I would like to make, this talk is mostly what the majority of the people put as their motivation slide. So your motivation slide is my whole talk. And in that regard, I would prefer if you ask questions as the talk progresses, because it builds up on its own. So if you miss something, then something later might be not particularly clear. So please raise your hand or shout or just ask a question, just because it might be easier that you can follow the material later. Another point I was going to make, this problem of marine ice sheets and their stability is more than 50 years old. There are very few people who really understand what the problem is about. So if you don't get it right away, it is rather my fault that I wasn't able to explain it well, rather than your fault. So please don't feel bad if something is unclear. That's why it's much better if you ask questions as we go. So first, a few basic facts about ice sheets. There are two big ice sheets presently on Earth. Greenland on the left, Antarctica on the right. Antarctica is about 7 times larger by area and more than an order of magnitude by volume. Both ice sheets cover about slightly under 10% of the land surface, not the whole surface, the land surface. During the last glacial maximum, at the maximum extent, there were many more ice sheets, and they covered about 25% of land surface. When ice sheets move around, they leave behind very spectacular landforms. This is a circle in Europe, and on the right, on the left, and on the right is a map of Finger Lakes that were left after Laurentide ice sheet retreated and disappeared. Ice sheets exhibit or have dynamics or exhibit behavior on a variety of timescales. Starting from the top left, it's the longest, something on the order of hundreds of thousands years. It's glacial, interglacial cycles. What you're looking at is the proxy, or rather inferred, ice volume change and the corresponding sea level on the right axis during the last 5 million years, and it's a reconstruction from the cores, various sediment cores, slightly shorter time scale on the order of 10 or slightly longer, 12,000 years. It's 100 QNs. It's discharge of debris from Laurentide by Laurentide ice sheet, and they are deposited by armadas of icebergs in the mid-Atlantic. So it's slightly shorter time scale. The next time scale on the order of 100 years, it's calving of large tabular icebergs. It's those large tabular icebergs on the order of hundreds or 100 by 10 tens of kilometers, and they calve about twice per century. This is a part of natural process of ice sheets and ice shelves in particular. So this is about 100-year time scale. Next time scale on the order of several years, it's inflation and deflation, or filling and draining of subglacial lakes on the active ice streams. So on the order of 3 to 5 years, such lakes collect water and then discharge into subglacial environment under fast-flowing ice streams. Another timescale associated with calving, it's calving from outlet glaciers, and it has seasonal cycle, and also the calving itself happens on the timescales of days, months, sometimes hours. The next timescale is the collapse of Larsen B ice shelf. So this timescale, it's about 3 weeks. Larsen B collapsed or went from completely intact to that what you see on the bottom left picture broken into smaller, much smaller pieces within pretty much 3 weeks. However, it is not the timescale of the ice shelf itself. The ice shelf was stable since last glacial maximum before it completely broke off and collapsed in 2002. The next time scale is tidal time scale. So the observations upstream of the grounding line on ice streams shows that ice flow can have, or rather has, a variability associated with tides. So this is on the order of days and maybe weeks. And the shortest time scale is on the order of minutes. It is associated with the stick slip phenomenon that is observed on Willand's ice stream. So what's happening, the ice stream sits for about 23.5 hours doing nothing completely. So it does not move at all. Its speed literally very close to zero. And in the next half an hour, it lurches forward with the rate, if translated into meters per year, it's about 10 kilometers per year. So this kind of stick slip phenomena that has this kind of bizarre behavior when the ice can move very, very far and very quickly, but only for a very short period of time. So this is the kind of overview of timescales that so far have been observed on ice sheets. So one point I wanted to make, that ice sheets are made from glacial ice, which is not exactly the same ice or quality of ice that you make in your freezer. It is not frozen water. So ice sheets are formed by compaction of snow and made of what's called meteoric ice, where meteoric refers to meteorological origin. So snow falls on top of an ice sheet that it starts to coagulate and create like more loose that snowflake structure and create into something more like bubbles that start to compact and effectively under its own weight. When more snow falls on top, the whole column is compacted into solid ice, but again, it is not the same ice which is frozen water. It is compacted snow. And for most part, meteoric ice is not transparent, and it's very opaque. If indeed there is a part which is very transparent, that implies that that ice was melted and water, liquid water was formed at some point, and then it refroze and created this layer of transparent ice. So on timescales, something longer than a few months or a year, ice is treated as non-Newtonian fluid. What that means that viscosity of ice changes with the applied stress, and it is shear thinning fluid. So it, and it also temperature, its viscosity, it's also temperature dependent. What you're looking at is the honey, specifically Manuka honey, that has somewhat similar rheology and somewhat similar viscosity, that blob with like it's honey cap, but actually it could be perfectly representative of an ice cap. Blood actually has quite similar rheology, so it also shear thinning and temperature dependent, so you're all related to ice sheets by your blood, effectively. Because of this behavior, ice sheets move. What you're looking at is the surface speed of both ice sheets, Antarctica on the left, Greenland on the right. If you can see my mouse, this is Jakobshavn Isbrae in Greenland, is the fastest glacier on Earth. It moves with about more than 10 kilometers per year. So although it is the fastest glacier, it's still nowhere near any ocean current or anything like that. So when people say glacial speed, it is exactly refers to quite low speeds in general. If we move to the right, these pinky areas in Antarctica, these are ice shelves. Ross ice shelf is over here and at the bottom of Antarctica, or in this particular map. This is Filch-Neroni, and here is Emery ice shelf. So again, if you take a look at the color bar, the variety or the spread, the range of speeds with which ice moves is quite large. So it's something that, say, less than meter or something close to a meter per year to up to 3 kilometers per year. So the variety is quite huge. Now, let's see how ice sheets work. So the left part of this diagram refers to Greenland, the right one to Antarctica. Both ice sheets are formed by accumulating snow on top. Then that snow, as I already said, compacts under its own weight. Then ice starts to move towards margins of ice sheets, where it gets lost either through surface melting, which is also called ablation, mostly in Greenland, and iceberg calving, or ice flows and goes afloat through the grounding line and forms an ice shelf, as in Antarctica. And the loss from the floating parts in Antarctica is mostly through sub-ice shelf melting and coloring as well. So ice flows under its own weight, meaning there is no other forcing apart than from body force, which is the gravity force. No wind stress, no currents, nothing. So effectively, if you put a blob of ice of substantial thickness or volume, it starts to flow. So that means that all boundaries of an ice sheet are moving boundaries. At the very kind of simplified level of description, there are 3 major components that require ice to start to float, or to that ice sheet floats. It's snow that accumulates, at the accumulation at the surface. And then the only 2 things that can oppose that spreading or flow of an ice sheet is the bedrock itself, because it's very irregular, and also basal shear, which is provided by the bedrock when you have friction at the bed. Now, again, if we start looking at the part which is called the grounding line, the discharge or transport of flux of ice that crosses it is the only contribution of an ice sheet that it makes to sea level. Because if ice is already afloat, that means by, as you probably know, by Archimedes' principle, it's already displaced its weight from the water. The bedrock of ice sheets that is below sea level, such ice sheets are called marine ice sheets. So a definition of marine ice sheet is an ice sheet whose bedrock is below sea level. And indeed, if you take a look at bed elevation of both ice sheets, Antarctica on the left, the huge part of West Antarctic ice sheet, and West Antarctic is determined or divided by the transantarctic mountains over here. So the quite a big part of West Antarctic ice sheet has bed elevation, which is below sea level. You can see the color bar over here. In Greenland, it's to much less extent, though the central part is below sea level as well. But the primary kind of, or the ice sheet, which is truly marine ice sheet, is West Antarctic ice sheet. So the only reason why ice shelves flow is because the density of ice is slightly less than density of water, or the density of ice, it's about 90% of density of water. If the 2 densities would be absolutely identical, there would be no spreading or no deformational flow of an ice shelf, and it would be just a translational flow as just advection what's pushed from the grounded part. So this is the place where ice goes afloat, it's called the grounding line. So, and if the two densities would be the same, that the surface of the ice shelf would be exactly at the sea level, and there would be no spreading or deformation. The tiny arrow, the red one arrow, is the only cause why the ice shelf flows or deforms, and it is that force is the difference between the two forces associated with hydrostatic and glacial static pressure, and again that caused by the very small difference between densities of the density of the ice and density of the water. Now let's move to the major, the main topic of this talk, marine ice sheets. As I already said, marine ice sheets are ice sheets that bed elevation is below sea level. This dashed line is meant to represent sea level. The place where ice goes afloat is called the grounding line. It's called XG over here. And it is determined by a very basic level by Archimedes principle. So the place where the thickness of the ice sheet is exactly as the bed elevation or the fraction of bed elevation, where the glacial static pressure and hydrostatic pressure are exactly equal, that's the place where ice goes afloat and forms the floating ice shelf. So the balance, or rather the behavior of marine ice sheet is determined by the balance of the accumulation through the surface. So A dot is the net accumulation or the integrated precipitation through the whole surface on the ice sheet, and the discharge or the transport of the ice or the flux of the ice through the grounding line. So the balance of these two things, the net accumulation and the flux through the grounding line, determines the behavior of marine ice sheet. And say if the two are exactly in balance, then the grounding line is in equilibrium and it doesn't move. It doesn't mean that the ice sheet is in steady state, because for instance, if precipitation changes with time, or it changes in general, then if the flux of the grounding line adjusts itself in such a way that it balances this accumulation, then the ice sheet is in equilibrium and the grounding line is in equilibrium as well. However, say the precipitation increases at some point of time, and then this net accumulation exceeds the flux through the grounding lines, and the grounding line advances to its new position, and that is determined by the imbalance, in the sense that the net accumulation through the whole surface exceeds the flux through the grounding line, making it to advance. The reverse situation happens when, for instance, there is not enough accumulation to balance this flux through the grounding line. And again, that might happen if you start with the equilibrium, that's the dashed contour, and then say precipitation changes, then it is not enough, the net accumulation, which is denoted A dot, is not enough to balance the flux through the grounding line. It is, so the grounding line then retreats to the left. Are there any questions at this point? Okay, if not, let's move on. So the obvious question then becomes, what is this flux through the grounding line? Because if one knows how it behaves, how it changes, then pretty much one can tell what is the dynamics or the behavior of the grounding of marine ice sheet in general. It's not the actually trivial thing to determine what it is, but nevertheless, it is, or rather the flux through the grounding line has been determined for a particular configuration. It is a steady state configuration of an ice sheet, and the whole configuration is unconfined. What that means that in the direction to the page or out of the page, there is no variation. So only variations that might happen, they are in this horizontal direction. And that the first who make some theoretical assessments or other quantitative assessments what that flux at the steady state as implies steady state or refers to steady state was Hans Weertman. He was actually a material scientist at Northwestern University, but he was quite interested in many questions in glaciology. So he inferred that the flux at the grounding line, if an ice sheet in steady state, it's proportional to the ice thickness in some power, which is with k is the exponent, which is larger than 0. Actually, it's greater than 1. So, and that means that in steady state, flux is an increasing function, monotonically increasing function of an ice thickness. Christian Schuf did a similar exercise for an ice sheet with slightly different assumptions, but nevertheless, he arrived to the same conclusion that in a steady state, an unconfined ice sheet has flux at the grounding line, which is an increasing function of an ice thickness. And this result allowed Weertman to infer that there are configurations of an ice sheet that are inherently unstable. So in what's known as marine ice sheet instability hypothesis, or as marine ice sheet instability, Weertman's marine ice sheet instability, that refers to an unconfined ice sheet in a steady state. So he says that an ice sheet that rests on a flat bed and situated below sea level, it's inherently unstable. And depending of the bed below sea level, the ice sheet either will shrink in size until it disappears, or it will grow until its age is at the bottom of the continental shelf. A stable ice sheet can occur if the bed slopes away from the center of the ice sheet. And the last sentence is my favorite. The generalization of our results to other bed shapes is rather obvious. That obvious thing has been hunting glaciology for more than 50 years. But let's see how his arguments work. So the argument goes, let's consider a steady state with this configuration in the middle. And the bed, what's called retrograde bed, so it deepens towards interior. Say we are in a steady state, meaning the flux through the grounding line is balanced by the accumulation through the surface of the ice sheet. If we slightly perturb this position of the grounding line to the left or downstream, then as Weertman asserted, the flux is proportional to the ice thickness in some power, then flux over here becomes larger than in its initial steady state. However, the net accumulation in steady state, and it is very important aspect that it is steady state because the precipitation remains unchanged because it's steady state, it cannot change at all. And because the grounding line moves slightly upstream, the flux through it is larger. However, the area through which that accumulation, the net accumulation occurs gets smaller. And as I showed on the previous slide, this means that the grounding line has to retreat again further and further down, and that becomes a completely unstable situation, meaning the flux through the grounding line continues to increase. The area through which precipitation is accumulated decreases. that causes the grounding line to continuously retreat. Now, if you take a slight look, if you take a look into the opposite situation and slightly perturb the position from the steady state to right, advancing, making the grounding line to advance, then again, because the thickness at the grounding line slightly decreases, the flux through the grounding line decreases. However, the extent through which the accumulation or precipitation is accumulated increases, meaning the net accumulation exceeds the discharge through the grounding line, and the grounding line keeps advancing. So on the retrograde path, and retrograde means that the slope is positive, or alternatively the bed deepens toward the interior, the marine ice sheet cannot be stable. So this is the Weertman marine ice sheet instability, but I'd like to emphasize once again that it's valid to a steady state. And a simple reason being, for instance, if it is not in steady state and we perturb the grounding line and it retreats a bit, but then if precipitation increases, then the net accumulation can perfectly balance the grounding line and make it in equilibrium as well. So, and conversely, if the grounding line advances a little bit, say precipitation changes and it slightly becomes slightly smaller with time, then the net accumulation and the flux can balance again, and the grounding line can be in equilibrium. Because of the simplicity of this expression of the flux, it's extremely tempting to use it as a parameterization of the grounding line dynamics in ice sheet models. There are several ice sheet models that do that. Probably the most known one is by David Pollard and Rob DeCanta. So they explicitly prescribe the flux at the grounding line and the function of the ice thickness. And the net result is that the West Antarctic ice sheet disappears for exactly this reason associated with marine ice sheet instability that I just described. So if the flux increases, is a monotonically increasing function of the ice thickness, and the bed deepens into the interior, the flux is greater than the net accumulation through the surface, and the grounding line keeps retreating, causing the West Antarctic ice sheet to disappear. But a few things should be noted. That one, as I already emphasized, the whole idea of marine ice sheet instability was determined for the steady state. Another aspect that is explicitly said by Weertman, that the ice sheet should rest on a flat bed, meaning it's extremely flat with very smooth with with no topographic variations, or if the topography exists, it's very gentle. And the same idea was in behind Schupf's study for his marine ice sheet. So the bed is extremely gentle and doesn't vary at all. The reality, of course, is not always as we like to have it in theory. And what you're looking at is the bathymetry or bed elevation of Antarctica with a zoom on the Amundsen Sea Embayment. This red line is the bed elevation through this transect, through this line, and the surface elevation is just from different data set. But nevertheless, what's apparent from this transect, that bed elevation varies quite extensively, on the order of several hundred meters, up to like 500-600 meters, on the order of like 50 to 100 kilometers. And if you recall, when I explained how ice sheets work and move, the fact that such huge variation, not huge, the bed topography itself plays a leading role in the flow of an ice sheet. If you wish, to a very basic level, it is the gradient of the glacial static pressure that drives the ice flow. So the question becomes, do these topographic undulations important, and how are they important? Well, apparently they are. So what you'll...
one moment, sorry. We have a question from Klaus.
Yeah.
Which is would you like to ask a question, Klaus, or?
Well, the question is whether sea level rise needs to be accounted because it uplifts the floating sea tongue and thereby might migrate the grounding line.
Absolutely, yes, you're absolutely right. So it's all relative to some sea level, some kind of datum, and if the sea level changes itself, the whole thing changes as well, because the elevation, the thickness at the grounding line, or as the bed elevation, is with respect to current sea level. So yes, if this dashed line moves up or down, then the location where the ice thickness is exactly as it's supposed to be in accordance with Archimedes' principle, it also moves as well. Yes, you're absolutely correct. Okay, so just to confuse you, I flipped the direction of the flow between, oh, sorry. This slide and this slide, but nonetheless. So this is a synthetic bed topography with some undulations on it. All these dots represent the steady state locations on the grounding line, and these two profiles just to illustrate how the ice sheet might look like for this particular locations. But the point I was going to make is that the flux at the grounding line is no longer a monotonically increasing function of ice thickness. It's rather an implicit function. So the steady state flux through the grounding line is an implicit function, and that meant to represent that it is implicit of the ice thickness and the bed slope as well. And if you take a look at the top right plot that shows the flux through the grounding line as a function of ice thickness, in the case of monotonical increasing, it should be something like this. But all these dots, as you can see, there is not much of a pattern. And if over here it's somewhat increasing with the ice thickness, over here it's actually decreasing. And if we compare the two fluxes, one which is for unconfined marine ice sheet with very flat bed, and this is the logarithmic scale. So the actual flux could be up to 2 orders of magnitude larger, or at least an order of magnitude smaller compared to that one, which is predicted by the monotonical increasing function of ice thickness on its own. So there are huge differences, and an obvious question, does that different dependence make any difference to the stability of steady states? And the answer is actually yes. So this black curve is exactly the same as this black curve. It's a bed elevation, but it is just plotted at slightly different scale. So all those circles are positions of steady state locations of the grounding line. So the open circles are stable positions according to Weertman marine ice sheet instability hypothesis, and the crossed one are unstable. So the slope that the bed that goes deeper in the direction of the ice flow, it's stable. If it's the elevation of the bed increases and is unstable, however, sorry, there are several positions that I actually define that rule, and this one corresponds to this one. So the bed slope is positive, and here is another steady state position which is unstable, but this one is seen to be stable, and the situation is opposite. Although the bed deepens in the direction of ice flow. This one is seemed to be unstable. This is was determined by gene linear stability analysis and determining conditions under which the ice sheet is stable or unstable. So just to have a sanity check, I did time variant simulations. What I I took the steady state configurations of the ice sheets. So these are steady state positions, and then just moved the position of the grounding line 1 kilometer upstream of it and let the whole system evolve, because the grounding line was slightly perturbed from its steady state position. It started to move, and the plots on the bottom show the grounding line migration, how it changes with time. So the one which is seen to be unstable or has to be unstable actually returns to its stable position, and it is stable. I just didn't plot. So it is stable, it just remains there. On the other hand, the one, this one, that according to Weertman's marine ice sheet instability should be stable because it's on downsloping bed, tried to advance to its steady state position, but then just turned away and retreated. So effectively, these two positions are in complete contradiction with Weertman's marine ice sheet instability. So
again, so you have a question from Stephen who's asking,
can
you give more detail on how you compute these stability points?
The way how steady state configurations were computed, actually it was like solving optimization problem or minimization problem. So it was not done time dependently, but exactly as a steady state, that in that position all conditions for a steady state configuration were defined, meaning I choose an accumulation rate and some basal shear, and then using that bed topography, what I showed over here, I was trying to find a place where the ice sheet is in steady state configuration for a given accumulation rate, for a given basal shear, and a given bed topography. The shape and obviously momentum balance, mass balance, and everything else has to be satisfied in such a way that the grounding line does not move. Does this answer the question?
Yeah, that helps a lot. But one more follow-up. Are you basically using the same physics as Weertman, but just paying more attention to the rough bottom? Is that the main take home?
Well, to the very basic level, yes. However, there are some differences. What I'm doing actually, it's exactly what Christian Schuh did. So what Weertman did, he assumed that ice behaved slightly differently, but in a sense, it does not change the picture. So he assumed that ice was plastic rather than viscous, but effectively, in terms of the momentum balance and mass balance, that does not make any difference at all. So if you wish, my kind of exercise is exactly the same as Christian Schuh did, but not on a flat bed or a very smooth bed, on a bumpy bed. That's the major difference. Everything else is even up to constants and like parameters of what he uses, what he used in his analysis. They are absolutely identical. The only difference is the bumpy bed.
All right, thanks.
Okay, so, but I'm fairly close to the end. So the point I was going to make is that in the last few years, more and more evidence emerges that marine ice sheet instability is rather an exception than a rule. For instance, it does not apply for confined or what in glaciology known as buttressed ice shelves. So there are papers on this. It does not apply to a configuration when that are more relevant to Greenland, marine outlet glaciers with part of it below sea level. It does not apply to these configurations. It does not apply if the basal shear is extremely weak even in the same configuration of unconfined ice sheet configuration. And if the stress is, if the basal shear stress is very weak, then again, the ground line can be both stable and unstable on any slope. So that brings me to, oops, where is summary? Here is the summary. I hope if anything came out from my talk is one thing, that contribution of marine ice sheets is determined by the ice flux through the grounding line. From the sea level perspective, it's the only factor that matters. As soon as the ice crosses the grounding line and goes afloat, it's done its job in terms of the contribution to sea level. Another point, that dynamics of the grounding lines is controlled by the balance between what's accumulated through the surface of the ice sheet and that ice flux through the grounding line. Weertman's marine ice sheet instability, it is a hypothesis, it is not an established fact. So it applies to steady states, and it requires and strongly relies on the fact that ice flux should increase with ice thickness. And it is a monotonic increase, meaning it cannot be a decreasing function whatsoever. Otherwise, it does not, the argument does not work. And again, it is valid only for steady state configurations. If, say, net accumulation changes with time in either direction, either increases or decreases, the ground line can find its balance because the two fluxes are balanced. In all other configurations, apart from very smooth bed, a steady state configuration in ice sheet is unconfined. Grounding lines can be stable and unstable regardless whether the bed slopes downward or upward. Presently, and there are no parameterizations can describe that dynamics. So unfortunately, all ice sheet models have to resolve it. So if, because if one puts a specific parameterization that relies on the functional dependence of the ice flux on ice thickness, there are unintended consequences that can lead to incorrect results. And that's about it. I'm happy to take questions.
Thanks very much, Olga. Do we have any questions?
I just jump in. This is Klaus Jacob again. You had pointed out initially that there are all these different time constants.
Yep.
Now sea level also has different time constants, from tidal changes to during storms to probably seasonal changes, and then in a unidirectional sense, sea level rise. How would, if there were to be accounted on these different time scale?
So in terms of the tidal,
let me ask the question.
Yeah.
How would the average movement of across the grounding line change if you just take the average of all those things in a long term, versus are there jumps of movement, let's say during high tide versus low tide and so on?
Just to make sure I understand your question correctly. So if we consider tides, indeed sea level can go up and down, and the grounding line, actually it is not exactly a line, it is a zone, it migrates. Yeah. So it goes slightly upstream and downstream with high tide and low tide. However, the frequency is so high that the flux through the grounded line does not have a chance to adjust to that new sea level that lasts only for a fairly short period of time, on considering the timescales that ice as a material is susceptible to. So one has to apply this in this particular case, or in the case you are considering sea level change, for some substantial, and by substantial, it probably on the order of years or decades, that the ice flux through the grounded line responses to it.
How about annual changes in sea level, which
change, sorry?
annual?
Oh, annual, okay.
Seasonal to annual.
I honestly do not know of any process that would result in annual sea level change. If you point.
Most tide gauges shows, I'm not sure in the Antarctic, but certainly on the US coast, we have in the fall on average a foot higher sea level than in the spring.
Okay, so it's seasonal. It's not annual, so it is seasonal. On these timescales, ice is still not very sensitive, not responding in that kind of dramatic way that the ground line kind of lurches, say, some appreciable distance or retreats back. Another point I need to make, that determining where the grounding line position is not a trivial task at all. The way how it is done, it is through observing the flexure of a floating ice shelf. So if the magnitude of that flexural displacement falls dramatically with the distance, then it is assumed that the grounding line somewhere around that position, because the floating ice shelf responds to tides and goes up and down and laterally it pitches and rolls and raises and falls with the tide. So if there is a bedrock below, then that, although the signal is present, the magnitude of such a displacement is significantly smaller. So, and then kind of something somewhat approximating between these two, if you wish, end members, then the grounding line is drawn or determined that over here is the grounding line somewhere. So in that regard, what you're describing as, say, seasonal variations in sea level, what is observed with tidal gorges, it might be in this error or in that noise level, which is very difficult to determine precisely the position of the grounding line.
We have a question from Stephen Griffiths and then Yao.
Okay.
Olga, yeah, thanks for the talk. When you said at the very end, the models have to resolve it when you're talking about the grounding line, can you give a sense for what is the scale of space and time that needs to be resolved?
Yeah, it's, if you wish, Steve, it's a talk on its own. So there have been studies that suggesting that the spatial resolution should be somewhere under a kilometer. And that under a kilometer comes from a characteristic length scale of an ice sheet, which is usually taken as an ice thickness. The ice thickness of the present day grounding Antarctic ice shelves at the grounding line is about around a kilometer. It varies, but roughly it is about a kilometer. So effectively, a proper scale, it is something smaller than one ice thickness locally, meaning if your ice thickness reduces, then the resolution should increase with that. So in terms of the time scales, it's slightly different question in a sense, what question you want to answer. Because for a steady state, for instance, then there is no time scale, which is steady state, and it's all about spatial resolution. And if it is something in terms of the, say, time variant simulations, in adjustment with the environment, then it is more rather about the ice flow dynamics and how long would it take to find the equilibrium position for the grounding line. And it really depends how far off when you start your simulation.
So do you think you need to resolve the minutes and hours stick slip
No,
physics?
no. By no
Okay.
means. No, this was just to illustrate that such timescale exists.
Yeah,
No,
okay. All right.
no, it is not. It is rather, yeah, that such timescale is present. But again, for an ice sheet model, which is mostly non-Newtonian rheology, then it is something order of month or, yeah, something like that.
Okay, thanks.
Yeah.
Yeah, you have a question?
Okay. Hi, Olga. I really enjoy your talk.
Thanks.
Yeah, I just have a naive question, more clarifying.
Sure.
So I was wondering, I saw your, I like the numerical experiment considering a bed slope effect, and where you showed that the stability of the grounding line is different from Weertman's result.
Yeah.
Yeah, and if I remember correctly, the implicit formula that constrain the grounding line flux is a function of the bed slope. Yes.
Yeah, this one. Yeah.
Yeah. So that involved the steady state grounding line flux. So in all your experiment, you're using a constant, you're using a steady state grounding line flux. Is that correct?
No, not okay. So let me explain this. So this QS, it's not the same as Weertman's or Christian Schuf. It is a steady state flux, which is consistent with this particular configuration of the ice sheet. So whatever flux through the grounding line, this particular value, it is an implicit function of other parameters. So by no means it, and that's why these plots over here, they show the difference. So that implicit, it's more like polynomial implicit function.
Mm-hmm. So when you, because at the end you show a evolution of the grounding line as a function of time. So along that curve, is the steady state grounding line flux also changing with time?
No, okay. So because it is time, I do not use any expressions for the flux. So this is done purely numerically, meaning I just solve the momentum balance, mass balance, and everything else with boundary conditions. No parameterizations of the flux are involved. And actually that flux in time evolving situation, it is different. It's that expression for the time variant is different than for a steady state. They are not the same.
Got it. Got it.
Yeah.
Got it. Thank you.
No worries.
And we have a question from Max Kelly, I think.
Yep.
Actually not. I realized my question doesn't make any sense. Sorry.
It's all right. You still can ask it, even still doesn't have sense.
No, I was just a little confused. Initially, you were talking about the changes to the catchment integrated snowfall accumulation, but I think that's not really the essence of the story of the Weertman hypothesis.
It is an important part of it, and that's why it's valid to steady state only. So because that flux, like through this vertical line, should balance whatever is accumulated over here. So yes, that accumulation is an integral part. Effectively, the steady state position is determined when the two are exactly equal. So, and it is not only, it is, first of all, it is equilibrium position. So in the grounding line does not move if this A dot and QG are exactly the same. However, that net accumulation it is allowed vary with time. The fact that is how fast that QG will adjust to that new accumulation rate.
Yes. Well, thank you. So my question might not have was not very precise, but does the size of the catchment area matter?
That's
for any of the questions that you are, for any of the questions that you are, the instability part of the story that you've been going over today?
Yes, so, and what I'm considering exactly, so it is a symmetric unconfined ice sheet. So it is exactly how it's drawn over here, meaning what this position, it's called ice divide, meaning what's happening over here, it's absolutely symmetric of what's on the left. So I'm sorry, on the right is absolutely symmetric what's on the left. So that position does not move. However, the extent over which the accumulation happens, it changes with the position of the grounding line. And that's exactly a point that all boundaries are moving boundaries. So the elevation changes because, say, the accumulation will change because you precipitate snow, and if ice would not move at all and would be considered as a block, as a cube of ice that does not move whatsoever, then that cube would just keep growing and the surface elevation would keep raising because you pour more and more snow on top of it. However, because ice flows and moves under its weight, the more snow you pour down, the faster it tries to spread through, and the wider it would like to be, to find and effectively the equilibrium position or a steady state configuration and such when there is no change in the surface elevation or in the horizontal extent. So your question is actually a heart of this problem, if you wish, meaning that the catchment area depends on the location through which that exact amount is transported through. So yes, it is a part of the problem.
So would a larger catchment be, more stable than a smaller one?
No, the catchment itself is the extent of that catchment is determined by the position of the grounding line. And again, that position is determined by where the bed is. So it is a balance, if you wish, of three parts. One, it's how much, it's the rate of precipitation, or how much you snow, the precipitation rate, then the extent of it, and then how much ice is transported through it. So if you have less precipitation, then the amount of it probably would be less, not probably, it would be less, and the grounding line position would be somewhere else, and the whole configuration would be different. Okay, let's see why maybe this curve would help to explain. So this is the same bed elevation, and actually the precipitation rate is absolutely identical for these two configurations. So however, this configuration, both of them are in steady state. However, this one is much larger because the grounding line position is over here. So in the catchment area is much larger. And in this case, again, the grounding line position is over here because the accumulation of the precipitation rate is the same. The catchment area is much, much smaller, and the ice sheet is much, much smaller. So these are two steady state positions for the bed configuration, which looks like this, and is exactly the same accumulation precipitation rate. But only because the catchment area is very different, their configurations are very different. Does it answer your question?
Yes, I think roughly, yes. Thank you.
Okay. We have a question from Jonathan Kingsley.
Hi, Olga. Yeah, fantastic talk.
Thanks.
My question, so your focus here was on the failure of the simple marine ice sheet instability in the case of large B sub X, or large bed slope.
Oh, yep.
And then on one of your final slides, one of the other ways in which it fails is when it's very slippery and you have a very weak bed. Yep. I was wondering whether, are those two results essentially have linked by, they actually had, How are those two linked? And I was wondering if it's essentially just down to form drag playing a larger part in the weaker bed.
Yes, it is about the form drag. However, to go in more into the details, the difference is in the terms of the momentum balance. So in terms of the weak beds, and again, I'll probably speak some jargon for many people, not particularly familiar, but it's very familiar for journeyers. So the balance between the divergence of the longitudinal stress and the basal drag, if they are on the same order, then you're on a weak bed regime. So and this is the balance between the two. In the case of this exercise that I just showed, the main balance in the momentum balance is between the driving stress and basal drag. The divergence of the longitudinal stress is small. So, and this is a major difference. It is two different leading order balances for the momentum balance. But effectively, you're absolutely right. The large or the bad topography, it is a form drag, and that's what, yeah, it changes the stability conditional here.
Okay, thanks. Thank you.
Do we have any other questions?
I guess I could just jump in again, Craig, and then ask Olga. So what's next then? If we've established that the simplified parameterization is not sufficient, do we abandon that approach and aim for, as you said, higher resolution, or is there any other form of attack on this problem?
It's a great question, but why the parameterization for in two dimension exists or not, I do not know, because I do know that developing a parameterization which is valid in one direction as considered over here, not plan, like not two dimensions in plan view, but just in flow line direction as it's done, it definitely does not apply to two horizontal dimensions. I can tell you that right away, why the it somehow could, the one dimensional could be tweaked in such a way that it fits two dimensions, I doubt very strongly. And the simple reason that ice flows not over the obstacles, but around them as well. That flow around changes the stress balance at the grounding line profoundly. So until somebody comes up with something that could be a parameterization of two-dimensional flow, then, you know, we wouldn't need ice sheet models. If you can parameterize two-dimensional flow, you solve the problem. So it's probably not a satisfactory answer to your question, but that's how it is.
Okay, do we have any other questions from the group? We're a little bit over time here, so we should probably, no, it's great, sign off. But yeah, thanks so much again for your great talk.
My pleasure. Thanks.
Have a good day, guys. Cheers.
Thank you.
Thanks, Craig and Olga. Bye.